Behold, a KUKA iiwa Fruit Ninja. Our project was inspired by the very popular game Fruit Ninja, bringing back plenty of nostalgia for us avid mobile gamers. However, what is often lost in history is its roots in the famous Fruit Ninja labor guilds in Osaka. A once very well-respected tradition and profession, it has since declined in popularity in Japan due to the lack of quality training and the increased availability of more lucrative careers. Thus, it opens the door for us to use our robot arm and fill these labor shortages. We approached this problem in 4 main steps. First, we needed to be able to describe the motion of the fruits, getting its position and velocity, with cameras. Then, using this data, we could calculate the possible future position of the fruit as it travels within reach of the robot. We could do this by using kinematic equations. Once we obtain a point to slice the fruit, we generate a cutting trajectory for the katana to follow and run kinematic trajectory optimization so that the iiwa arm could execute the movement. In order to generate random fruit trajectories, we decided to randomly generate a point within reach of the iiwa and randomly generate a starting position under the robot. Then we used kinematic equations to set the initial velocity of the fruits. This way, the fruits would appear to be flying upwards into the robot's view.
To actually get the robot to cut fruit, we first had to generate a trajectory for the blade. If there was one fruit present in the workspace, we draw a straight line from the robot's current position to the fruit. If there were 2, we draw a straight line between the 2 fruit. We then ran kinematic trajectory optimization, which include position constraints for the start, end, and fruit cutting position. We'd also add a duration constraint to the trajectory. There'd be orientation constraints added to specific points based on how crucial it was for the blade to be oriented a particular way. So you can imagine for cutting points, it was really important that the blade was oriented at a certain angle. It was also faster and more robust than inverse kinematics.
Okay, so now we'll be focusing on the perception system, which is used to identify and track fruits as they are launched towards the robot. So as I said, we have an Intel RealSense camera, which is an RGBD camera. We can extract the point cloud given the RGB and the depth images. And so given this image here, we can then extract the point cloud. Given the fact that all the fruits are different colors, we can then filter these point clouds to then identify the points corresponding to a specific fruit. So as you can see, we have the RGB image, and then from this we can extract a mask which represents specifically the points for the red fruit. We can do this again for the green fruit, and so on and so forth, and we can do that for the blue fruit and any more fruits that we have. And then now that we have this, we can average the coordinates of the points to get the x and y centroid ordinates. And so another important metric is the performance. And so we measured the mean error of the centroids that we expected versus the centroids that we actually computed. And we saw that this was 0.035 meters. This was extremely small and was 4 times smaller than the diameter of the fruits themselves. And because it's such a small relative distance, it will not affect the trajectory of the katana, and it will still allow the katana to slice through the fruit. This was a consistent result with an extremely small standard deviation, and we saw that whilst this mean error did increase to 0.07, it only increased for large fruits, such as fruits with a 0.4 meter diameter, and so it's still relatively small, and whilst it does increase the fruit size, it increases with fruit size, and so it's always relatively small, and so this is not an issue for us. Another metric to consider is the timing, and we saw that as we increase the number of fruits that we can process by increasing the number of colors we filter for, we have a linear relationship with the time required to execute the perception algorithm. However, this is still always extremely small, and we can see that we can identify 49 fruits within 0.3 seconds, which allows us a fast enough sampling rate for the rest of our code.
Combining all our systems together, we were able to create a robotic arm that was able to play Fruit Ninja and cut fruits that came in flying from different directions with different sizes and different orientations.